One way of using the de Broglie hypothesis is to assume that electrons behave like waves, and that these waves are trapped inside the atoms. When they're trapped, they form standing waves, and this can be used to explain why they only exist with certain energies. You need to know the derivation. So explain the origin of atomic energy levels in terms of the electron in a box model. This first example here, we have a wave, like a guitar string for example, which has a node at either end. We're able to get half a wavelength in there. So here is basically, there's only half a wave there. Between the ends here, that is one full wave, or basically two half waves. So the next one is basically two halves of a wave. Then the next one is three halves of a wave, and so on, four half waves, and so on and so forth. So remember this idea of standing waves. There are only a certain number of waves that are allowed between ends. In this case, it's an integer number of half wavelengths. You can't have 3/4 of a wavelength because then the boundary conditions are not satisfied. In this case, we have to assume that the ends are nodes. So we only get a certain number of waves. In other words, only certain wavelengths will be allowed inside this atom. So in an atom, we consider these electron standing waves as being confined in an atomic box, and we visualize it as being these waves which are curved around the nucleus, a bit like this. And as they oscillate, this will be a node, that will be a node, and this will be an antinode and an antinode, and so on. Since we'll only allow certain waves, we only get certain wavelengths. And if you remember, the de Broglie hypothesis is that the wavelength is equal to h divided by p. So since we have only certain wavelengths, we're only going to have certain momenta and therefore certain energies. And here are some examples of the wave in the box standing waves. So basically the electron behaves as a standing wave because of the only certain waves are allowed, only certain kinetic energies are allowed, and we have to know the derivation. E is the kinetic energy, m is the mass of the electron, L is the length of the box, h is Planck's constant, and n is the number of half waves. So here we have it. This is the length of the box from A to B. And if you remember that it's only a certain number of half wavelengths, so n lambda over 2. But we need to rearrange in terms of lambda. So lambda is equal to 2L divided by n. Now remember also that the de Broglie hypothesis is that lambda is equal to h divided by p. And if we substitute in the wavelength there, which is a wavelength which is 2L over n, into here, we end up with p is equal to h divided by 2L over n. Let's simplify that. Since we're dividing by 2L divided by n, we can take the n to the top. So we end up with this. Now, we're halfway there now. We can look at the kinetic energy. The kinetic energy is half mv squared, but it's also p squared over 2m. But this is p. So we substitute this value for momentum, and then we simplify, since we're dividing by 2m here. We end up with n squared, h squared over 8m L squared. And this is what you need to remember as a derivation. So we have this equation. What will this look like if you plotted n against e? Well, as you increased n, e increases with the square of n. So the bottom energy level will be here, the next one will be a little bit bigger, and then we take bigger and bigger jumps as we move up. It's like the energy ladder for a hydrogen atom, but inverted.